Hello. Today we're going to be looking at some handcrafted assembly programs, one from me and one from a programmer whose GitHub profile picture is this, so you know it's going to be good. The one from me will be using special assembly parallel instructions to go super fast, so that's going to be good too. 6 years ago, I had a manager who was known for being inscrutable. He wasn't trying to be, he just naturally thought about things in an unusual way. Once, when I asked him for feedback, he described me as being really good at analysis, which was curious to me because neither I nor anyone else described any part of our job as analysis. I asked him what he meant and he refused to clarify. Analysis, he said, that's what you're good at. Today, I know that he was right. Writing the script, I know that I must now describe what analysis is. So I opened my favorite etymological dictionary and I found that analysis is two smaller things joined together. Ana meaning up, back, or throughout, and lysis, or something like that, which emerges from loosening or cutting apart. Analysis means literally to loosen something and break it apart into smaller pieces. When we apply analysis to complex things, we're breaking them apart into simpler elements. This, of course, is exactly what I've just done with the word analysis in order to understand and then explain it. It's my reflex action towards everything. Technical educators often remark on the usefulness of reading code, and I found this nice in theory but lacking in practice as guidance for learners. Reading is for most people just passing over a text and letting it create images in your mind, and it's much more rewarding for people who know a lot about the domain. I instead recommend analysis. Through carefully picking apart a program written by someone or someone's else, asking how it works, why this way and not that, contrasting it with your own instincts, and eventually, typically last of all, identifying potential shortcomings, you can mine an almost bottomless well of insight, both from the traces that the author left and from the core truths of the field itself. So it's taken us 7 videos, but we're doing reaction content now. But the reactions are going to be good. We're going to start off with a program by Eli Bendersky. It counts words. I realized in the editing process that the sections with the command line debugger are not really the best way of illustrating the program running in the video. I've tried to clarify them a bit, but if you find they jump around a bit too much, just focus on the diagrams and the algorithms. Algorithms in assembly are particularly interesting because you're writing them often with the bare minimum of help. So if you want to count words, you can't use regex or splitting things apart or anything like that. You have to figure it out yourself, which is a lot of fun if you like programming. See you for the next bit. We're going to look at a program called WC-X64. It's an x86-64 assembly reimplementation of the command line tool WC, which stands for word count. This is the version of WC from the GNU core utilities. It does a few things. It counts the lines, the words, and the characters in one or more files. It prints them out in a line against the file name, and then it prints out a grand total. It can also read from standard in, but we're going to focus on the files scenario today. Now let's make and run the assembly version. You can see that it does almost the same thing, except with a little bit more padding. I think the GNU WC will handle numbers of varying lengths and pad with spaces accordingly, while this one doesn't, hence the extra space. This version of WC was written by someone called Eli Bendersky, so thanks Eli. Assembly is pretty verbose, so it's a fairly long file, and we're going to go through it from a few perspectives. First, I'm going to talk through a diagram which explains at the high level how the program proceeds and is structured. Then I'll go through the main procedure in the debugger so we can explore how it works, and then do the same with each function. Finally, I'll talk about some of the line-to-line syntax features that Eli uses and that I quite like. The program works like this. Firstly, it works out how many arguments it's been given and then goes through them one by one. For each one, it opens the file, delegates to count in file to count the elements, adds those elements to the grand total, prints a line to standard out, closes that file, and then loops around to the next file. When it runs out of files, it will print the grand totals and then exit. The functions can be split up into data processing and data formatting functions or subroutines. Count in file does the data processing and print counters does the formatting and output along with a few friends. We'll talk more about how they work later. The program starts with a section for constants and a section for data. They're fairly well named, so we'll pass over them and into the main procedure, which we're going to look at now in depth. I'll start up the LLDB debugger and set a breakpoint for the start label. I then kickstart the program with run and land on line 65. When a Linux program starts, it has an integer representing the number of arguments it's been given on the top of the stack, and then beneath that, an address to each argument. Line 64 moves the data at the stack pointer, which is the count of arguments, or argc, into the register rbx. When we print this out in the debugger using regread, we can see that the value is 3. Now, if you look up at the top, you can see that I actually gave the program 2 arguments, not 3. The first argument given is always the name of the executable itself, and then all the arguments after that, so 2 plus 1 or 3. On line 65, the program compares RBX, the number of arguments, to 1 to see if the program has been run with files as arguments or not. If it has no extra arguments, it branches off to read from standard in. Since we've given it 2 arguments, it just continues onwards. It uses XOR to zero out registers R13 through R15. They're already 0 here as it happens, but it doesn't hurt to be sure. Assembly programmers often use XOR to set a register to 0 rather than MOV, since the instruction in x86-64 is a little smaller in the machine code, and XORing a value against itself always gives 0. We now prepare to go through each file in turn. We set up RBP as the counter, starting at 1 rather than 0, so that we skip the first argument, which is going to be ./WCX64 as discussed before. This rather fancy instruction on line 81 uses some slightly counterintuitive syntax to calculate the memory address that we need to look in to find the address of our file name, so there's 2 layers there. The instruction then puts that address into the RDI register. This type of addressing is called scaled index addressing. The upshot is that you take the base register, in this case RSP, then we add in a displacement offset, then add to it the index register multiplied by the scale factor, in this case RBP times the last 8. This looks kind of odd, but it's actually very useful. This instruction allows us to look at the stack address in RSP, skip past the first item with that displacement offset, then index into the stack with the RBP register like an array, assuming that the items are 8 bytes long. In any case, it gets us the address of a C string containing the first file name. You can see that since it's a C string, it ends with a null byte. We move on and open the file with a fairly ordinary open syscall, ignoring any file that won't open. That syscall then returns to us a number called a file descriptor, which we'll need to reference if we want to read from that file later, which we will. We save it on the stack using push. Then we call count in file, more on that later. It returns 3 counts in 3 registers, which we then add to the grand totals in registers R13 through 15, and also move into the registers ready for our next call to print counters. Having called that, we pop the file descriptor off the stack and then use it to close the file. Incrementing RBP and looping around then gets us the address of the next file, which we go through the same process with. Finally, we move around a few registers and call print counters again to print out the grand totals and exit. Now let's look at count in file in more depth. First, I'm going to talk you through the algorithm in a diagram. We've got 3 things to count: lines, words, and characters. Characters are easy because the read syscall already tells us how many bytes it's read from the file, so we just add those numbers together as we read the file. For lines and words, we use this algorithm. First, we get a byte indicated with this arrow. We check if it's a new line character. Since it isn't, we don't increment the number of lines. Then we execute a state machine. I'm not going to go into too much detail on state machines, but you can imagine a state machine as if it's a system that can be in one of a number of states, and we can keep track of the state to then do things when that state changes. This state machine is very simple. It can be in one of 2 states, in whitespace or in Word. When the state machine transitions from in whitespace to in Word, we increment the word counter by 1. We start off in the in whitespace state, and this character is not whitespace, so we update the state machine to be in the in Word state. Since this has just triggered our transition from in whitespace to in Word, we add 1 to the words count. Then we get the next byte and do the same thing. It's still not a new line, and it's a non-whitespace character, so we don't change the state. We get the next byte. Still not a new line, but it is a whitespace character, so our state machine changes state to in whitespace. However, since this transition is from in Word to in whitespace, we don't trigger our transition action and we leave word count alone. We get the next byte, still no new line. It is a whitespace character, so we keep the state machine as is. The next byte isn't whitespace, so we update our state machine to be in Word, which triggers our action to update the words count. Then we proceed through a few more characters and we get to a new line. This triggers us to update the lines count. It's also a whitespace character, so we update our state machine. The next character is 2, so we leave everything as it is. Finally, we have an X character which triggers us to update our state machine and consequently our word count. Our final count is 1 line, 3 words, and 11 characters. Now you might be thinking at this point, wait a minute, Kate, where I come from, that's 2 lines. The first one says hi you, and the second has that X on it. You've only counted 1 and you've missed the second one. Well, funnily enough, not only does this algorithm only count this as 1 line, the GNUWC also only counts this as 1 line, which I guess must have tripped some people up at some point. Not me though. And it's all the more reason to end your files with the new line. Let's look at how this plays out in assembly. We define our constants for our state machine and set up a few registers. We load the address for the buffer that we're going to read into and then set our initial state to in whitespace. We execute our read syscall, which populates our buffer with the text of our file, or part of it if our file is bigger than our buffer. You can see this reflected in the memory of the buffer here. We update our character counter with the number of bytes read, and also use that to determine if we've read the whole file, in which case it would be 0. Since it isn't, we move forward. We read the byte using scaled index addressing as before. See if you can figure out what this one evaluates to. I know it might seem strange, but it's actually really nice for using memory as arrays, and the more I look at it, the more I understand, like C pointer type signatures, the arguments to malloc, struct alignment, and all that stuff makes a lot more sense when you look at this particular kind of instruction. We read the byte and its value is 41, or the character code for an uppercase letter A. It's not a new line, so we move past this conditional jump. It's not a whitespace either, so we fall through all the conditions until we get to the logic for handling non-whitespace characters. We look at our state machine state to see if it's already in Word, and if it isn't, therefore it's in whitespace, we're going to execute our transition from in Word to in whitespace. We increment our word counter in R15 and then set our state to in Word. Then we jump to done with this byte, which increments our counter, checks if we're at the end of the buffer, and if not, jumps back to the start. Our next character is also a non-whitespace letter. I'm going to set a breakpoint on line 208 to help us jump easily to the next iteration of this loop and look at the character code. Now we've got a space, which isn't a new line or a carriage return, but it is a space. So we jump to lscene whitespace not new line. This checks to see if we're in a word, and if so, we jump again to end current word, which just sets our state to in whitespace without touching the counter. It then falls through to done with this byte to end the loop. I'm now going to update our breakpoint to still be on line 208, but to only break if register DL is the new line character. We continue execution and it works. Following the execution through, we jump down to scene new line, which increments the line counter and then falls through to the same whitespace logic as before. Remember that these jumps aren't ifs, they don't return or jump around by themselves. Execution's just going to keep going downwards until we tell it to jump somewhere else. I think Eli is using this assembly fall through behavior quite idiomatically here, if we can say such a thing about assembly, and it's, to me, very elegant. Finally, we move the counts to their right place to return and then do the returning. And that's the counting function. Let's now look at print counters. By itself, it's not too complicated. The main complexity is in the I2A function, so when we get to that, I'll diagram it out so you can understand the algorithm. We kick off the program again and set a breakpoint at print counters. We set up the function by storing any registers we need to restore later onto the stack. We're going to use R15 as the counter variable for which counter we're currently on. That's lines, words, or characters. We start by setting up a buffer or an area of memory for our function I2A to use. We're going to fill it with spaces by delegating to another function, memset. These functions, by the way, I'm fairly sure are modeled after common parts of the C system libraries. We need to blank out the buffer because we're going to reuse it for each counter. When we get to a later counter like words, the buffer is going to contain the old value for lines. And since I2A doesn't write all the bytes of the buffer, just the ones that are involved in the actual number itself, we might end up with leftover digits from the last number if the previous number was longer than this one. So for example, if we were printing out 1 million first and that got put in the buffer, and then we wanted to print out 10, we'd end up with all the digits of 1 million kind of stuck on the left side, which would be no good, so we need to blank it. Now in most cases, of course, a file is going to have more words than it does lines, so this isn't going to matter, but it's not necessarily the case. It might be a file of 5 million empty lines and no words, in which case you're going to mess up. So it's best to be certain. Memset isn't anything special. It loops from the start to the length you've given it and then writes the byte you gave it. In this case, you can see the bytes in the area of memory have gone from null bytes to ASCII spaces. Having done this, we return and get ready to call I2A, which by the way stands for integer to ASCII. Now I2A takes two arguments. The first is the integer we want to convert to ASCII, and the second is the address of the last byte in the buffer. That's where our least significant digit will go at the end. Almost. In fact, a null byte will go there. But before that, the last digit will go there. So we pass these items in and call I2A. I2A begins by writing a null byte at the end to construct a C-style null terminated string. It also handles minus numbers by taking note that this is a minus number and flipping it positive. Though there's not much likelihood of minus numbers here, it's a nice touch which makes this function more reusable in future. To tell you the rest, I'll switch to a diagram. Here's how it works. We take a number, in this case 1337, and an address to the end of a buffer. We start by writing a null byte to terminate the string. Then we divide the number by 10, store the result into the same place, and then keep the remainder. The remainder is then going to be a number 0 to 9. We store this number as an ASCII digit into the buffer. This is done in the code by adding 48 decimal or hex 30 to it. Then we decrement the pointer and perform the same operation until the number is 0, at which point we return. We're essentially just breaking off the last decimal digit each time. The real I2A does broadly this. It uses the divide instruction, which puts its quotient into RAX and the remainder into RDX. So we clear RDX first and then execute the division. We then write the digit to the buffer by decrementing the pointer, adding hex 30 to the register, and then moving that register's value into the buffer memory. We can see the 5 show up here. We then do the same thing another time to get the second digit, and then we find we've printed the whole number, so we can finish up with the minus number logic, return, and move on. Print counters then sets itself up to delegate to print cstring to print the buffer to the terminal. Print cstring does this by first searching the buffer for the null byte terminator, which therefore gets to the end of the string and it's already got the start. It then uses this address and the length to make the syscall for write, and you can see it's now printed to the terminal in amongst all of our debugging messages. We then return, do the same series of operations with the other two counter numbers, and then print the file name if we've got one. Remember, we got a pointer to that in the arguments to this function. And that's print counters and pretty much this full program. Pretty nice. I said I'd finish up this section by talking a bit about what I liked about this program from a code quality standpoint. They're all fairly ordinary code quality principles, just applied really nicely to assembly. The program's broken up into clear sections, which is actually to me reminiscent of quite old languages like COBOL, which would enforce code being broken up into sections like this. There's a constant section, a data section, a section for the main routine, and then a section for subroutines. In assembly, this is really valuable because, much like Lord of the Rings Old Entish, it takes a long time to say anything in assembly. Eli uses constants heavily to make the many magic numbers in assembly much more readable. Think of syscall numbers, stream numbers, buffer lengths, characters, and so on. They're all really well specified. Eli also imposes a really strong procedural structure on the program. For control flow, he uses these local labels, which are conventionally prefixed with .l_ as opposed to the labels for functions which aren't prefixed. When it comes to indentation, I'm typically a 2 spaces person because it's better for screen real estate in videos, but in assembly I will definitely concede that 4 spaces makes much more sense. Since there's essentially no nested structure in assembly, there's very little chance of running off the edge of the screen. Plus, using 4 spaces lets you sneak tiny new labels into the left-hand side if you need them. Eli also uses functions very effectively to control complexity in the main routine and in larger functions. See, even if you're a cracked super engineer at Google writing raw assembly just for fun, you can still break up complex routines into simpler subroutines. They're also often just a little bit more useful than WC really requires. For example, while it would be impossible to have a minus number in any of these counts, the subroutine that converts numbers into ASCII strings still supports them. Since, once again, it takes a long time to say anything in assembly, I think this is really good practice to improve code reuse. Eli's comments are also really nice, both at the function level and line to line. It makes this program much easier to understand. Since we have far fewer opportunities for naming in assembly, and we often have to do lots of fiddly little operations, using comments really liberally delivers a lot more value than in high-level languages. So there's quite a bit that we can take here when it comes to good code style and structure in assembly, so thanks for that, Eli. For one of the exercises later on, I ended up porting WC x64 to ARM64 assembly, and in the process I actually realized something that I missed. There's a part of the program where we need to print out the 3 counters, lines, words, and characters, and around that part he pushes those counters to the stack and then reads them out again. I was staring at this like, why on earth is this stack logic even here? He's got the numbers in the registers, so why put them in the stack? And the reason, or at least the reason that I guessed, is that you can't iterate over 3 registers in assembly. You'd need to repeat the code 3 times. So instead, he pushes them to the stack and then iterates over the last 3 slots in the stack using scaled index addressing. You could, I guess, also extract another function and pass in a different register each time, though it does seem a bit less elegant. So I thought it was pretty cool and interesting that even after all this time staring at that code, I still skimmed over something which porting the code forced me to understand. So a fun little extra exercise if you're interested is porting some code from one architecture to another. You learn quite a lot about both architectures that way. Next, we're going to look at processing data in parallel using single instruction, multiple data instructions, which I'm going to in this video call SIMD for some reason. These were introduced to everyday computing architectures in the 90s to accelerate the new multimedia processing craze. They're a way of processing multiple chunks of data simultaneously and thus faster without using multiple threads or GPUs. I wanted a project that would give us an excuse to cover them, and I found one. Now, I'll tell you about it. I also used the visual debugger this time, so I think it comes across a little better. To understand single instruction multiple data or SIMD style parallelism, we're going to start with the special registers that the ARM64 architecture makes available for SIMD purposes. I actually don't know if anyone pronounces it SIMD. They might just say it out the whole time. I'm going to say SIMD though, because I'm definitely not going to say SIMD for this whole video. Most modern processor architectures have a SIMD dialect. In ARM64 it's known as Neon, which is also nicer to say. So in this architecture we've got 32 of what are known as vector registers, named V0 through V31. If the word vector isn't that familiar to you, just imagine that they're called array registers. These registers are 128 bits or 16 bytes wide, in contrast to the 64-bit registers we saw before. We can actually interpret these registers in a variety of ways. For example, either as one big long 128-bit value, 2 64-bit values, 4 32-bit values, 8 16-bit values, and a few others besides. These different layouts are called arrangements, and they're determined using little arrangement specifiers stuck on the end of the register when you refer to it. Some instructions will let us use only some of the arrangement specifiers and not others. So, for example, if we want to add one vector to another, we can specify add V0 arranged as 16 8-bit long parts to V1 in the same arrangement and put the result into V3. These little sub-values are typically known as lanes, and hopefully you can see why here. So vocabulary-wise, we've got 32 vector registers which can be accessed in a number of different arrangements. An arrangement specifies the number of lanes and their size. A vector instruction, known in ARM64 as a Neon instruction, processes the value using these lanes. In this instruction, each lane of one register is matched with the same lanes of the other registers, but this isn't always true. Some instructions will mix and match them for useful purposes. I was looking for a project to tackle using SIMD and I settled on this one. Try to beat the Unix TR utility to uppercase a text file 100 megabytes long. TR takes about 4.5 seconds to do it, so that's our target to beat. It would also be cool if the technique we used could be easily repurposed to do other things like lowercase or translate other characters. Here's one approach we could take. We could load some data from memory into a vector register, move hex 20 or decimal 30 into another vector register, and then subtract. Since ASCII uppercase characters are all 32 places lower than their lowercase equivalent, this uppercases the string. It does work, but it also destroys any uppercase characters, or in fact any non-lowercase characters in our string. So it's cool, but it's not super practical. We need to be a bit smarter than this. I did consider an algorithm that uses vector level comparisons to check whether each character is within the lowercase range, and then use multiplications and additions to sub 32 from only those bytes, which I think would work, but I found another way which I think is better. There's an instruction in Neon called TBX. TBX takes a source register, a destination register, and up to 4 registers which make up together a lookup table. And this lookup table is really just an array of up to 64 places, each of which can have one value. TBX then goes through each lane in the source, gets its value, goes to that index in the lookup table, and then puts the result of that lookup into the lane in the destination register. Usefully, if the value is out of bounds, so the number in the lane is larger than the number of spots in the table, it will leave the lane in the destination unchanged. Here's an example with a friendlier version of ASCII that I've just made up. This version of ASCII has only 52 codes, one for each lower and uppercase letter. First, we load the source text into the vector register, and then we load a table with 32 spots in it. We craft the table such that when TBX looks up the value of a lowercase letter in the table, it will get the value of the uppercase equivalent. So for lowercase o, which is value 14, if we go to index 14 in the table, it maps to 40, which is the value for uppercase o. I'll show you an iterative version of this. We flip to the next lane, which has a lowercase f in it, or value 05. We look up value 5 in the table, which maps to 31. We then write value 31 into the destination register, which you can see now corresponds to the uppercase F. This works. Plus, while I'm showing you an iterative demonstration here, the processor will actually be doing these operations in parallel, or at least that's what it advertises. So, since it processes 16 bytes at once, it in theory should be 16 times faster than going through character by character. This doesn't help us with mixed case or other characters yet, and this is made up ASCII rather than real ASCII, so let's work on it a little more. Here's an updated algorithm. First, we create 4 64-byte long lookup tables. Each table will cover a 64-point slice of the 256 point long ASCII range. For most of these points, each lane will map to the same value, sort of, as you'll see shortly. We load the source data into another register and then use TBX to translate the first 64 code points into exactly the same numbers. In this case, hex 20 is the only value that falls within this range, so it's the only one that gets converted. Since TBX leaves alone all bytes that don't fit in its range, the others are left empty. Then we take the source register and subtract decimal 64 or hex 40. This gives us a mangled string, but it'll be useful for our next step. In our next step, we use table 2 to map. Table 2 is like table 1, but it has two differences. The first is that instead of mapping 0 to 0, it maps 0 to 40 hex. This means that it'll end up mapping, for example, uppercase letters back to the original code points they were before we subtracted hex 40 from them. The upshot is that we're translating almost every point back to what it was before the algorithm ran. Essentially, we're shifting ASCII down by hex 40 in order to process it with this table that can only store hex 40 number of values. So we need to add hex 40 back to get it back to normal. Except if it's a lowercase letter. If it's a lowercase letter, or rather a lowercase letter minus hex 40, it will translate that into its uppercase equivalent code point. Like before, if the value is out of range, for example, this space here, it gets left alone. So with 4 iterations of these tables, we can convert any ASCII code point to any other ASCII code point. Our algorithm can definitely translate lower to uppercase, but in theory it can also do other character translations too. Now this takes 16 vector registers just for the table, and then an extra 3 for the input, output, and subtracting registers. 19 in total. That's quite a few, but they're there for us to use, so we may as well use them. And honestly, a little surprisingly to me at first, this all works in code too. Let's take a look. We'll breeze through the code first and then run through it in the debugger. We've got a little preamble, some constants, thanks Eli, and some handy macros, which I would definitely recommend using in assembly, by the way. It's a real lifesaver if the overhead of a subroutine makes it kind of pointless to break out. A macro is essentially a little template that you can give arguments to, and then it gets substituted into the code wherever you put it. Annoyingly, they do have to come before the code that uses them, so here they are at the top. Now we've got our main procedure. I've broken it up into a few sections using local labels. I'm actually not 100% sure if the .l_ prefix has any meaning in Clang, but I thought it looked nice, so I've stolen it from Eli, but with 2 underscores because it aligns nicely with the instructions. These are the little things that bring me joy in programming. Anyway, we first load up the lookup tables into memory, which takes a few instructions. The table is in the data section and it looks like this, basically all the numbers 0 to 255. The only change from the standard ASCII sequence is that I've replaced where the lowercase letters would be with some uppercase letters. What we end up with is a table of 256 values, each of which maps to its index, 0 to 0, 1 to 1, etc., except for the block representing lowercase characters, which maps to the numbers for uppercase characters. So when we use this lookup table, the result will be uppercasing everything. Skipping back to the code, we've loaded the map and our offset register. We have a section for loading the buffer from standard in, and then a section for processing that buffer in chunks of 16 bytes, which is the max we can fit in one vector register. We'll see this work in a minute. We then have sections for advancing through the buffer in chunks of 16, flushing the buffer to standard out, and then exiting the program. I extracted reading standard in to a function too, although honestly it looks a little lonely down here. Let's fire up the debugger. If you got this far, you'll probably have sat through me using the terminal-based LLDB, so I think we both deserve a bit of a treat. I'm going to use the code LLDB VS Code extension to step through it graphically in the editor. Our first breakpoint is on the first instruction. We load the address of the map into X19, which we can see reflected in the watch section on the left. When we run this LD1 instruction, you'll see that V16 through V19 all change to incorporate the values in the table. We do this 4 times to load 16 vector registers full of tabular goodness. And next you'll see V0 get filled with 64s or hex 40s. Now we load our buffer. We use a few registers to keep track of the start, length and the end of the buffer. Probably this could be simplified if I thought about it enough. We branch to the read standard in function and you can see the buffer get filled on the left. And I thought today we'd process some of Shakespeare, just to give it a bit of extra shouty oomph. Let's process a chunk. We're going to load 16 bytes of our buffer into V1. You can see the bytes directly, but to give us something extra to look at, I've used some Python watch expressions to show you the string that is inside the register right now. You can see this on the line just below V1. Right below that, I've done some processing to highlight which values in the string are in bounds to be translated, the lowest 64 values. Here you can see that the spaces and the comma are in bounds to be translated next. When we run tbx, you'll see that those values get copied into the destination string, which you can see just below v2. When I say copied, I mean they went through this whole lookup process, but it ends up exactly the same values. Next, we subtract 64 from v1. This mangles the string, so we can't read it as ASCII anymore, but in the third row below v1, I've added a view that lets us see the values that are now in bounds for being translated the next time. It's all the letters upper and lower. Now, when we run tbx, you'll see that those get copied in too, but uppercased because they've gone through our translation table. We process the high 128 bits of extended ASCII, which we probably don't need to do, it's just for completeness really, and then we store the result back into our buffer. You'll see this appear on the left. Next, we advance our buffer by 16 bytes, which you can also see skip along on the left, and check if we're at the end, and since we're not at the end, we loop back to process another chunk. Let's speed through a few chunks and skip ahead to the point where we print the buffer out. We do this and you can see our new shouty Shakespeare appear in standard out. That's just the first buffer though, there's plenty to go, so we loop back up and read another chunk from the file. Skipping ahead to the end, we see the end of the file. Though not the end of the play, of course, I wouldn't want to spoil you on the ending to Romeo and Juliet. Nobody spoil it in the comments either. So, how fast is it? Does it beat TR? Well, we've got our 100 megabytes of letters here, and when we time cat and TR together, we get 4.452 seconds overall. When we run hours, we get 0.281 seconds overall. And that's about 15.8 times faster, which makes sense since we're processing 16 bytes at once, so roughly 16 times faster. Pretty cool. We can also check the output is correct in that it matches TR and test the correctness on some more realistic real-world text. Now, if you've written anything like this before, you might be wondering about buffer size. Am I just using a really large buffer to slam TR into the floor? Well, it's not true. I couldn't work out what TR's natural buffer size is, so I guessed probably 124 bytes was a minimum bound. So I think I'm probably using about the same size as TR or smaller. So you could increase this buffer size and get some further improvements at the cost of memory usage as well. So if the Royal Shakespeare Company ever comes up to you and says, we're going on stage in 10 milliseconds and our actors can only read uppercase, now you know what to do. And now the exercises. This, like every video, has a page on the OODS website with resources and exercises for you to do if you want to dig into this topic yourself. I'm indebted to all these resources for making this video possible, in particular Eli Bendersky's WCX64, which I also ported to ARM64 for anyone who does the next exercise on Apple Silicon. We've got a bigger exercise today, which is to clone one or the other versions of WCX64 or ARM64 and make some changes to it. Working on somebody else's code gives you a lot that building your own from scratch doesn't, and it's a good stepping stone to be able to do this work professionally or to contribute to open source projects. In this exercise, you've got 3 steps: correcting the line count, identifying line endings, which has a few different technical decisions for you to make baked into it, and then counting integers, which will give you the opportunity to build a more complex state machine. Or you can just kludge it in, I guess, but don't blame me if it gets messy. And as always, there's an extra exercise for OODS members who I deeply appreciate for supporting me to do this work. If you'd like to join, there are several big buttons on the website which will point you in the right direction. Next time, I promise you, this is my accountability, we will get into or onto the stack. I almost got it into this video, but I didn't quite make it, so next one it is. Once we've covered the stack and memory layout in a program in general, we'll be only a short distance from crafting our own executables, which is our little milestone for the moment. Okay, that's the last scripted bit of this video, and also this light has clearly been on. I say on, the sun is on the whole time, so epilogue. One thing I wanted to work into this video just as a brag, because I have not ever enjoyed exercise. It's been not a problem, but it's been a source of deep, well, I'm going to say middling shame for most of my life. But I recently started weightlifting, and I can now lift an uppercase. This is the joke I meant to work in somewhere. I can now lift an uppercase A's kilograms in, well, deadlift 4 times though, so not that many times. Still uppercase A, so I think it's pretty impressive in ASCII terms. Probably be more impressive in imperial terms, but I don't know what that is. Yeah. Anyway, this was a fun one, and I'm definitely starting to sweat in this light now, so I'm going to finish it here. Have a great week.